Hello there. My name is Iro Tanshi and I'm the TA for Dr. Mcintyre's class on statistical analysis of ecological communities. And I'll be talking about other forms of biodiversity today, exploring phylogenetic diversity and functional diversity. When we assess the biodiversity within a community, the first intuitive measure is to look at species richness. How many circular species are there, how many triangle shaped ones, how many star shaped species. But there's a bit more information in the system beyond just species richness, because as we know, the triangles may all be related, and the oval shaped species may also be all related. In fact, we know that species that are, say, square-shaped, for example, may function differently from star-shaped species. And so when we compare two communities, what we're really doing is comparing beyond how many species there are. And so we're really looking at how many species there are between both communities, how many species, um, how are the species related within each community, and how do they function. So these are the things we're comparing between communities. In the late 80s, with the development of molecular techniques and their implications for conservation, many authors started to argue about the efficacy of the use of species as units for conservation. In fact, the argument that taxonomic uh, diversity is quite limited because it assumes that species are equivalent, when in actual fact, the species differ in terms of their functionality as well as their evolutionary history. But also, many authors raised the point that selecting a species or site for protection is arbitrary and meaningless without some sort of measure of distinctiveness or ability to adapt to future situations. But again, taxonomic diversity and taxonomic measures are quite limited at uh, quantifying and capturing that distinctiveness. I mean, there are other issues that we're not going to get into, but at least these are the key ones. So it's now commonplace to measure these three forms of biodiversity. In fact, most papers these days will report taxonomic, functional, and phylogenetic diversity. Well, I went ahead and did a Google search, and I was looking at how popular these terms have become in the literature by looking at how many hits we got on Google Scholar. And between 2011 and present day 2021, multiple dimensions of biodiversity have increased from 31 hits to over 250 hits. That's a magnitude of increase. Similar situation with phylogenetic diversity, and more so with functional diversity, because functional diversity is also used in other contexts beyond the multiple dimensions of biodiversity. Now let's briefly examine phylogenetic diversity. So phylogenetic diversity was invented and popularized by Daniel P. Faith in his 1992 publication that has now gathered over 3,500 citations. And in fact, what the metric does is that it quantifies the sum of branch lengths within a phylogenetic tree. So using this tree as an example, say that's community A and this is community B. If you wanted to quantify and compare the phylogenetic diversity between both communities, all you need to do is to sum up the total lengths of the branches. So branch C, B, and A, as well as the length of their nodes. And that gives you the total the total phylogenetic diversity for that community. Same thing with phylogenetic diversity within community B. And basically, this is how it works. There are other measures of phylogenetic diversity as well that we wouldn't get into for this class, but just so you know, there are measures out there beyond Fate's phylogenetic diversity. So if you've never built a phylogenetic tree before, you do not need to worry, okay? Because the experts have basically done the work for us. There are tree building programs online. You probably just need to find your sequences and find maybe a tutorial to walk you through that program. But there are programs that allow you prune a super tree and prune the species that you want or that are within your community that you're interested in out of a super tree, and then you work with that. You already have a tree. You don't need to do all of the hard work. In the past, I've used Phyloty, but some of that data is now outdated, and I am now working with the VirdLife program that has got trees for super trees for mammals, birds, amphibians, and there's a fourth group that I cannot remember at this time. But it's really fun when you're not building the tree from scratch. Because I built one in my former life, and uh, it's not really not nearly as bad, but it's way fun to just prune a tree when you need it. And the way VertLight works is that you put in a couple of species that you want and you set up the parameters, a couple, 3, 4 things, put in your email, and within 10 minutes, sometimes you get a response, depending on the size of the tree, obviously, and I guess traffic to the site. But it's a really cool project that allows you to do all kinds of amazing work these days, which 5 years ago was not even, well, 5 years, 10 years ago wasn't really possible. So, all of the data that were, well, the tree that we're going to be using in the exercise came from the VertLife project. You should check it out. It's really cool. Well, moving on to functional diversity. So very briefly, functional diversity really attempts to sort of describe and assess or quantify how energy flows through the system. And what we're really looking at is that you're trying to cover the range of functional traits and functional groups within a community. So for bats, bats are, ecologically diverse, the most ecologically diverse mammals. And they're really hyper diverse in many areas, especially in the tropics. And so you're looking at, bats, say, bat diet, for example, is one of the traits that you're interested in. And there are other traits too. There's locomotion, flight, there's echolocation. There's all these different things that you can line up for bats that really get at how energy flows through the system and is functionally tied in with the way bats or whatever group you're interested in use the environment, say with their diet, how they move, how they do all of this amazing stuff that animals do. So there are two approaches to quantifying functional diversity, and the first one really looks at a functional group approach where you basically assign species to categories, either based on diet, locomotion, or whatever functionally relevant, say, behavior or pattern that the species or groups use. And so you use that to assign species, but it's much more suitable for large scale types of analysis because it's okay to not be too specific at that scale. Um, But there's also the functional trait approach, where you're basically measuring, so deriving numerical values for functionally relevant traits, such as traits that may be related to locomotion. You do foot length or wing length. Traits that may be related to some aspect of diet, like say bite force, how hard the animal bites on its prey, or indeed things like echolocation frequency that tells you details about, say, for bats, how the animal finds its prey. And this functional trait approach is much more appropriate for small spatial scale work, and sort of site level comparisons. So some of the more common functional diversity indices are functional richness, functional evenness, divergence, and dispersion. And I'm not going to go into all of the detail for this. Try to find the definitions. I was going to provide a glossary of terms, but I decided to let you explore. So now we're going to go on to the exercise, really just playing with data, some of it from my work, some of it from Steve Kimball's work, um, with our package that he developed to help address some of these questions. So the data we're going to use today comes out of my master's, where I was collecting bats across 3 localities in Nigeria. And this is where Nigeria is in Africa, if you don't know where Nigeria is. And I was basically just surveying across localities in the south using mist nets. And I surveyed bats bi-monthly over an 8-month period. And these are some of the species that I picked up, some really cool fruit bat species. And I'm not showing the insectivorous bat species here, but there's also insectivorous bat species that I collected. And I've described some of that data in the notes. So I've also described the localities as well. I was working within just one state in the south, and that's Edo State. And there is the national park down here, Komo National Park, which is also well, undisturbed forests at this point. And then there's Emu, which is basically an entirely covered in agricultural cropland, and Osaso, which is really a Guinea savanna, was referred to as a Guinea forest savanna mosaic system, where there are patches of forest interspersed with some form of grassland or sparse woodland, but it also has farmlands in that area that I sampled. So that's kind of the localities that I worked at, and I collected those bats. And we're going to explore using some of the phylogenetic data that I downloaded from the VERT Life project, and some of the data that I collected during this survey. So the first step we're going to take here is, as you know, will be to prepare the data, read it in, check that things are as they should be. We're going to be using the libraries ape, Picant, I want to say Picante, and FD. And what we're going to start off with will be to reading the phylogenetic tree, inspect the tree, and convert the tree to a philo object. And if you've gone through the notes, you're going to see all of these steps laid out. But we're also going to put in the community data, check it out, make sure it's as it should be, as well as the trait data. And then we're going to check that the species labels are the same across data sets, because this is the one thing R would do. As soon as you start to combine all of these data sets to do all the analysis that you want to do, and there's just this tiny error, you know how R throws things off. If there's a space or a hyphen somewhere where you shouldn't be, then the analysis just doesn't run, just because it cannot match stuff. And so, speaking of matching stuff, there is an actual function to make sure that everything matches. So it's going to match the species names or species labels, excuse me, on the tree with what you have on the community or the sample data set. And if there are species that are not uh, on one or the other data set, it's going to drop those. And in this case, I've retained all of that type of error within that data so that you can see how if you don't run that match function to match data sets, you just end up with an error. And if you do get it to work, you would get that report stating what has been dropped off to allow the analysis run. So you're gonna see that in the analysis if you haven't already done so. So we're going to measure phylogenetic diversity, and that's the second step of the exercise. And what you're really just doing is measuring Fate's PD using the function PD. Now, that's all we're going to do in this exercise as well as in the assignment. But there are a number of things to keep in mind just for your, extra knowledge, so to speak, or when you're playing about with your data, some of the things to recognize is that you're going to need to compare your observed data or your observed values to null expectations, and you're going to do that using the SES-PD function. And what that just does is that it computes a number of model outputs, more or less, and what it's really just doing is excuse me, is sort of checking for the effect size of your data, your observed PD versus the null populations, and whether or not that is significant. So that sort of tells you how different, whether your observed values are different or not from null expectations. And that combination of the z values, as well as you're going to see the results when you run it, assuming you do, which you can go ahead and find that on the package. Download the PDF description of the I believe it's a Pecans package, or the APE package, I can't remember now. Anyway, you download that and you go through the tutorial, the PDF of the package, and it will provide you with codes at the end of each of those. If you know how it works. If you don't, then this is for you. If you know how it works, ignore me. But anyway, it will provide codes for you to figure out how to use SES, and it really isn't. It's not tedious at all. As soon as you figure out your data's clean, everything's pitch perfect, you just pop in your analysis using those codes, and you should be fine. But then, there are other types of indices that people measure with phylogenetic diversity. And there is the nearest taxon distance as well as the mean pairwise distances. And, these are all sort of specific to the type of questions you're asking. So if you want to ask a certain type of question, you sort of look through the literature to see how people are addressing those questions. And it does line up for your type of question. For some surveys or some types of studies or questions, indeed, you're fine. You're good to go with just PD measurements. Now, the third and final step of the exercise is to compute functional diversity. And what you really need to do is just to use the db fd function. And what that does is it computes multiple functional diversity indices that you can then pick and choose. Well, technically, you have to report functional richness for sure, and functional evenness. Anything else that you do after that is really up to you in terms of what you're interested in. People will typically report functional dispersion and functional divergence, um, but they're they're very complementary indices, and again, it's up to you. Um, there's even the community weighted mean of traits, and it's up to you to use that if you're interested in that. But in terms of sort of just quantifying all these three measures of biodiversity, this is a demonstration of what's possible. So what you want to do, at least as far as just exploring the results of this analysis, is to examine both the functional diversity and the phylogenetic diversity values and see whether they match up with taxonomic diversity. So does taxonomic diversity match up with functional diversity matching up with phylogenetic diversity? In other words, are the sites is the site with the highest species also the one with the highest functional diversity and highest phylogenetic diversity? Um, so you kind of want to check this out. So functional richness to PD to species richness, because you would also get species richness values reported on the side. Um, well, if you check this out, what does it tell you about the relationship between these indices? And it could be one thing or the other. It's really up to you to just sort of infer and evaluate what you're seeing. Well, so that's the end of the lecture, and I just wanted to show off some of the bats that we've got in Nigeria, and it's part of the uh, is part of the one of the publications that I just submitted. So it's really fun to just behold these bats, and I can't help showing them off whenever I get the chance. Well, I guess I will see you Thursday.